Okay, YouTube, in this video we're going to explore a couple of pretty hefty theorems in algebra here, but these are the fundamental theorem of algebra, which just sounds like it's pretty important here. This word fundamental is pretty clutch, but also the linear factorization theorem. So let's go ahead and visit the fundamental theorem of algebra first. It says if f of x is a polynomial of degree n, so in other words we have this nth degree thing, and we say that our degree has to be at least 1. Then the equation f of x equals 0 has at least one complex root. And so essentially what I want you to see here is that there's kind of a corollary to this, a kind of a thing that follows this statement here. But if we say it's nth degree, and this is something we wrote down in the last video here, but we say nth degree if and only if, maybe I'll write this here, if and only if, exactly n roots. I'm going to write that word here, exactly. And I'm going to write this, n complex roots or zeros or solutions. And so basically what this means is if you are a complex zero, remember you can be a complex number and be the number 3. You just be 3 plus 0i. You could also be a complex number and be 3i, which would be the same thing as 0 plus 3i. Or you could be a complex number, of course, like 3 plus 2i, for instance. But if you are any of these things here, then we could basically say, well, let's just put it this way. If you're nth degree, then you have to have exactly that many answers. That's all that means right here. Okay. So the linear factorization theorem, when we look at this, it says if f of x is this long polynomial function here and it's in standard form, so this means that a sub n, of course, is our leading coefficient, and n is our degree. We always kind of label these things here. Not that we need it, but this is also our constant term back here. But if we had this long polynomial function, the linear factorization theorem says at least if your degree is at least 1 and your leading coefficient is not equal to 0, then really your polynomial function can be rewritten in this way. And so basically what I want you to see is that we have a sub n. We're going to label this again here. This is our leading coefficient. We're saying that our function can be rewritten as the leading coefficient out in front times all of these different factors. And so we say, well, how many factors are there here? And we say, well, we have x minus c1, whatever this c1 is here, x minus c2, all the way out to x minus cn, where n, remember, n represents our degree. So what this theorem says is this. Essentially, I'm going to switch over so that I can type here for you guys because my handwriting just looks very poor here. Let's put in some text right here. Ooh, that's very large text. I wonder if I can go down here. And nth, I'm not really sure how the font got set on that. Thanks for being patient with me here. Let's do, this can't be that much worse. There we go. That works. Okay. An nth degree polynomial can be, since I'm going off the screen here, can be written as the product of exactly n linear factors. Okay, so here's what we basically mean here. It means that if you know the zeros of a function, then you sort of know the factors. Because when we factor a statement like f of x here, we say f of x equals this x minus k times the quotient that we got left over here. We multiply these and we set this equal to 0. Remember, what we're doing is we're taking each individual factor and you're setting it equal to 0. And not that I care much about what the quotient is in our, maybe division problem here, but if I set this equal to 0, remember that x equals a k is a 0 if and only if x minus k is a factor, okay? And so that's essentially what the linear factorization theorem says. It says you can write any degree polynomial, nth degree polynomial, as exactly n linear factors where we have x minus that complex 0 going in each spot. So we're going to use this to our advantage here. We're going to leverage this. I want to show you how this is something that is beneficial when you want to write, say, I guess, a polynomial with given zeros. As a matter of fact, let's just do this. Let's take a look at this graphically. What if we were to make a polynomial, and I know that I want it to have zeros at +1 and +2. So when I write my factors here, I'm going to write this as x minus 1 and x minus 2, because if I had set those equal to 0 and solved them, then I would get zeros for those. So looking at my graph here, I can see that at 1 and at 2 I certainly have zeros. I could interweave this all the way down the number line here. We could go x minus 3. Look at our picture here. X minus 4 is another factor here. So this would be some 1, 2, 3, 4. So 4 linear factors multiply out to be a 4th degree polynomial. And right now our leading coefficient is 1. And I can see exactly where these zeros are at exactly the spots that I wanted them to be at 1, 2, 3, and 4. So let's play with our leading coefficient here. If I make our leading coefficient 2, look at our graph here, 2. Let's go with 3 this time. 3, 4, 5. We can see that we still get our vertical stretch even if I make this negative. How about negative 2? We get our vertical stretch and it opens downward. Or we could look at this as an x-axis reflection. Or we could look at this as, because the leading coefficient is negative, I know the right side of my graph must fall. And because it's 4th degree, I know the left side of my graph has to have the same behavior as the right side of my graph. So you can see that this linear factorized form is really kind of a beneficial form because you can see the leading coefficient out in front and you can basically see the zeros. So here's the thing we're going to aim to do in this last part of this video here, is basically if I give you the zeros, could we work backwards to write the function that was associated with those zeros? So yes, we can, of course. So we say write an equation for a 3rd degree polynomial. So we have n is 3, 3rd degree polynomial. Having zeros x equals negative 3 and I. So a couple things we want to say here. First of all, we have to have 3 linear factors multiplied together. 3 linear factors on our polynomial. So we're going to say this. We're going to say f of x is equal to our leading coefficient times x minus this, x minus this, and x minus that. That's kind of sloppy. I want to establish this right off the bat because this is the most important part of this video, is that the linear factorization theorem says that we have to have exactly 3 linear factors here that multiply out to be this polynomial with some leading coefficient. So we'd say x equals negative 3 is one of my zeros. Look what happens when I put this in here, negative 3. When I rewrite this on the next line here, essentially we're going to have the leading coefficient times x plus 3. So you know what? You can write it like this. But you can also say that because negative 3 is a 0, x plus 3 is the factor. We get that. But as far as this goes, we say we have a 3rd degree thing. Aren't we supposed to have 3 solutions here? So the other part of this video is essentially that because I have an I here, and this is really, we could rewrite this as 0 plus I, then I know that 0 minus I, or its conjugate, must also be a solution. And the reason why is because complex conjugates occur in pairs here, or complex solutions occur in conjugate pairs. So when we fill these in here, we're going to write 0 plus I and 0 minus I, or I'm just going to write positive I and negative I. So when I rewrite this here, we have x minus a positive I is x minus I, and over here x minus a negative I is x plus a positive I. So we get all of this. And so one thing I want to do here is I'm going to basically tell you that I want to neglect the leading coefficient. We're going to treat it as if it's a 1 right now, and then we'll go back and put that back in there later. But for right now, we have this polynomial function f of x, and I can tell you that these have to be the zeros because I've written it out as the product of 3 linear factors, each of these representing our zeros of this function. So here's the part we need to do next, is basically simplify. So simplify by multiplying out. So I'm going to start with these 2 factors here, and the only reason why is because they're conjugates. I know that when I multiply conjugates, I get a difference of 2 squares. So I'm actually going to write that right now. That when I multiply these 2 conjugates, I get this difference of 2 squares where this x part is like our a part here, so x squared. And then the I part, whether it's negative or positive, I'm just going to go with the positive here, is our b part, and I just said go with a positive because I know I'm squaring it anyways. So we get this, we get x plus 3 times x squared minus I squared. Remember that I squared is the same as negative 1, so we get x squared minus a negative 1, which gives us, and it's a lot of simplifying here, we say x plus 3 times x squared plus 1. So now we're going to FOIL this here, and we'll be left with our final polynomial here. We say x to the 3rd plus a single x plus 3x squared when we do our inner, and then plus 3. So essentially we get this when we put this in the standard form, x cubed plus 3x squared plus x plus 3. I'm going to put a big box around this right now. And I'm also going to go type this into Desmos. Let's do that. We say x cubed plus 3x plus x plus 3. Whoops, not spot, it's fine. So we had f of x equals x cubed plus 3x plus x plus 3. And let me see if I have this right here. X cubed plus x plus 3x squared, let's see, x cubed plus 3x squared plus x plus 3 plus 3x, that would be squared. Okay, so looking at this, we see that we have a 0 here at -3, and -3, looking at this, was one of our zeros. And we say, well, what about the other two zeros? Whoops, yikes, guys, sorry. The other two zeros are these imaginary ones right here. So when we say, does it actually hit the x-axis? Well, no, it doesn't hit the x-axis at those other two, but we still get this third-degree polynomial with a 0 exactly where we wanted it. So now going back to what we had done here, which was scratch out that leading coefficient, what I hope everybody can see is that technically f of x is this a sub n times all of these other, this a sub n that was out front. It was out front, out front, out front, out front. It should be out in front of this. And so it is out in front of this, and we say x cubed plus 3x squared plus x plus 3. The idea is that we didn't know what the leading coefficient was. So in this follow-up question here, it says find the value of the leading coefficient an in the last equation if f of 1 equals 8. And remember that f of 1 equaling 8 is the same thing as us saying when we plugged in 1 into our function, we got 8. So we're going to go plug this in for x and y respectively. I'm going to go plug in now here for y. I'm going to plug in an 8. And I'm going to say I don't know a sub n, but I do know over here that x, we can plug it in and get a value inside here. So when we plug it in, we say x was 1. It's going to make our job a lot easier. We get 8 is equal to a sub n. 1 cubed is 1. 3 times 1 squared is 3. Plus 1 plus 3. 2 3's and 2 1's give us an 8. So we get 8 equaling 8 times a sub n. So a sub n here equals 1. So really our polynomial function, when all is said and done here, is 1 times all of this stuff in parentheses here. So I'm just going to write 1 times and then just my x cubed plus 3x squared plus x plus 3. And because this was all this times 1, I'm just going to write the 1 out in front here. But here's our polynomial function with these given zeros. So the important thing to take away from this is if you have the zeros, then you can write it as the product of exactly n linear factors. Cheers.